Hello everyone. I'm very glad to meet you. My name is Hamid. I work as an assistant in the Department of Mathematics at Novosibirsk State University in Russia. As the main organizer, I'm honored to welcome to the second workshop on domination theory and its application. Thank you for coming. As we know, domination is one of the most studied topics in graph theory, and so we decided to organize the series of workshops on domination theory in the Mathematical Center, which is located at Novosibirsk State University in Russia. And our aim is to share the recent results in developing domination theory. We organized the first workshop last year in November, and we invited 5 speakers from Iran, Poland, Spain, Malaysia, and India. This workshop contains 6 invited talks by given great researchers from Iran, France, Spain, China, and India. Since the workshop is supported by Mathematical Center, I would like to invite Professor Timur Nasaibolov to join us. He is in charge of Deputy Director of Mathematical Center. Timur, can you hear me?
I can. Yes, I do. I hear you.
Timur. Okay, Timur. We would be happy to listen you.
Yeah, thank you. So, good morning, dear colleagues. First, I would like to thank you for coming to this second workshop on domination theory. So, I'm very glad that it's already the second part of this event, and I'm glad that there is a huge geography of this event. And yeah, I don't want to waste a lot of your time, but anyway, I would like to give you a couple of words about Mathematical Center in Akademgorodok. It's kind of the main organizer of the event. However, first I would like to underline that we are the organizers. However, the main organizers are our researchers, and mainly Hamid, who introduced me. So let me tell you a couple of words about Mathematical Center in Akademgorodok. We work on the basis of 2 organizations in Novosibirsk. The first one is educational organization called Novosibirsk State University, and the second one is a research organization, scientific organization called Sobolev Institute of Mathematics. So Novosibirsk State University is one of the best universities in Russia, and here I give you some information about our university. So it's top 5 in Russia, top 117 in the world, and it is located inside Novosibirsk Akademgorodok. So it is strongly connected with research institutes. So, and our department of Mathematics and Mechanics, is the biggest department of the university, and we have more than 1,000 of students, and in total we have 8,000 of students. So, and here you see some information about our department. So it is strongly connects education and research. If we speak about Sobolev Institute of Mathematics, where we do research and where our students do research, it is the biggest Russian research institute in mathematics by the number of employers. There are more than 200 researchers. So, and here you see some statistics. Maybe it's not very interesting, but what is interesting is this part. Here in Sobolev Institute of Mathematics, we have almost all areas of mathematics under research. And the domination theory, in which you are all specialists, is not very strong in our university. However, we have combinatorics and graph theory, but domination theory and graph theory is just a new area which is just started to there's some specialists appeared in our university. That's why I'm very glad that you are here and that you exchange your knowledge and your results and discuss like future results. So if we speak about mathematical center in Akademgorodok, who is based on two organizations, then we have four main areas, four main directions of activities. The first one is our principal direction is fundamental research. Is research which is devoted to the developing of mathematics as a whole. So here we have 16 research groups, and one of the research groups is the group where Hamid works. Hamid is the main organizer of this event, and so he's doing graph theory in our center. So the second part is applied research, and by applied research I mean the research such that the results of this research are applied immediately after obtaining of this. So usually we do it together with industrial partners. Here you see some of them, and we earn money on this. So the third part is education, and I don't want to speak a lot about education here because this event is not educational, it's more scientific. So, but here I have to say that we do both long-time educational programs and short-term courses. And maybe the most interesting part for you is the organization of events. So we organize a lot of events, and maybe here again I have to say that these events not organized by administration of the center. It is organized by the researchers, like Hamid organized this event. So that's it. That's all I wanted to say. Maybe the part which you need the most is the information about this event, and maybe you can want to participate some of these events in the online format or in the face-to-face format. So if you are interested, you can visit our website and to read more about the center and maybe some events which you can participate, to give a talk or to listen other talks, to have discussions, and to obtain new results. So here I would like to stop and yeah, to wish you a nice event, good discussions, and nice contacts. That's it. Thank you.
Right now, I would like to invite the first invited speaker, Professor Saeid Alikhani. He works at in the Department of Mathematics at Yaz University. Professor Alikhani, can you hear me?
Yeah, yes.
Okay, we are looking forward to listening you. Thank you for coming.
Okay, thank you so much. You're welcome. Hamid, we have, I think, 5 minutes to.
Yes, we have 5 minutes.
start.
Let me introduce you.
Okay.
Okay. Professor Saeid Alikhani is a great researcher in the field of dominating set in graphs. He has published many good articles in this field, and I think about I don't remember the number of your articles. Said
About 200.
200,
Yeah.
yes, 200. Okay. And okay, would you please share your screen?
Okay. Okay, so thank you so much, Hamid. It's okay? Hamid, do you see my PowerPoint?
Yes, I see.
Okay. Let me to check my pen. Is it Can you see when I write on the power or not? I think no.
Yes,
No,
I
no.
see.
Okay, okay. So you can see when I write in the PowerPoint.
Okay.
Okay.
Okay, as we see, the title of your presentation is counting fair dominating sets in graphs, yes?
Yes. Okay. Thank you so much, Hamid, and thank you, Timur, and another organizer of this workshop, to invite me again to have a present here. And thank you so much. I would like to talk about fair dominating and fair domination number and the number of fair dominating sets. Okay, I think we can start now. Hamid, is I think, is it okay that I start?
Yes,
Is it
yes,
fine?
you
This
can
time?
start.
Okay.
Yes, you can start this.
Okay, yeah, let me to define the domination number. We have a graph G. We say a set D is a dominating set if every vertex which is not in D is adjacent to at least one vertex in D. In other words, the open neighborhood of V intersection with D is not empty for every V which is not in G. And the domination number is the minimum cardinality of a dominating set in a graph. If you let me, I want to turn off my webcam, maybe because of
Okay, okay,
the situation
okay.
of internet.
Okay.
Is okay?
Yes, it's okay, yes.
Okay.
You-
Okay, as an example for dominating set, you see here a simple graph that has 11 vertices, and you see the black vertices 1, 8, and 10 is a dominating set for this graph because every white vertices is adjacent to at least one black vertices. And obviously this is a minimum cardinality of the dominating set, so the gamma of this graph is 3. In other words, the domination number of this graph is 3. As you know, most of the papers published in domination theory determine the exact value of domination number or obtain some upper and lower bound for this parameter. And before 2008, there were no paper concerned with enumerative side of this problem. In other words, no paper about the counting the number of dominating set of graph. Me and my supervisor in my PhD thesis introduced the domination polynomial of a graph that, you know, this polynomial is generating function for the number of dominating set of graph with cardinality I. So we have a polynomial here, which denoted by d, g, and x, and this is equal to sigma dgi xi, where this notation dgi denote the number of dominating set of a graph with cardinality I. For example, you see here a a graph P5 with 5 vertices, it is easy to see that the domination number of this graph is 2 because, for example, we can consider the vertex 2 and the vertex 5 as a dominating set, and this is a minimum. So the gamma is 2, and now we want to count the number of dominating set with cardinality 2. As you see here, we have 3 dominating set with cardinality 2, 1 and 4, 2 and 4, and 2 and 5. But for example, 1 and 2 or 1 and 3 cannot be a dominating set because, for example, the vertex 5 cannot be dominated. So the number of dominating set of this graph, this G is P5, but with cardinality 2 is 3. And you see the family of the dominating set of P5 with cardinality 3, that we have here 8 dominating set. So the number of dominating set of P5 with cardinality 3 is 8. And obviously every 4 vertices of this graph can be dominating set of P5. So the number of dominating set of P5 with cardinality 4 is 5 choose 4, which is 5. And we have just one dominating set with cardinality 5, which is all vertices of this P5. And so the number of dominating set of cardinality 5 is 1. And so we have this polynomial x5 plus 5x to the 4 plus 8x to the 3 plus 3x to the 2. This is a very simple example for domination polynomial of P5. There are many results for domination polynomial. For example, you see the domination polynomial of a complete graph Kn obtained by this formula, and domination polynomial of a star can be obtained by this. And there is a recursive formula for domination polynomial of paths. As you see, we have a recursive formula of order 3 with these initial values. And also for the cycle, we have a recursive relation for domination polynomial of cycle with different initial values. And for domination polynomial for product, but some product of graph has studied in the literature. For example, for the join of two graph, you know, the join of two graph denoted by G1 v G2 and is a graph with vertex V1 union V2 and A set E1 union E2 union with all edges joining V1 and V2. So, for example, this one, the vertex, the set V1 is the vertex set of G1, and this is the vertex set of G2. Any vertex here connect to all vertices in the G2 and versa. Okay, this is a formula for domination polynomial of join of two graphs that you see here. And for another product that, for example, corner of two graphs that you know, I'm sure that all of you know the corner of two product that denoted by G circ H, and is the graph arising from the disjoint union of G with the number of vertices of G copies of H by adding edges between the ith vertex of G and all vertices of H, a copy of H. And this is a formula for domination polynomial of corona of two graphs. And you see here, this formula is independent to a structure of graph G. It just is dependent to a number of vertices of graph G. Okay, to obtain a general recursive formula for domination polynomial of a graph, we need a definition, which is a vertex contraction that denoted by G/U. And in this operation, we delete the vertex U from the graph and join all vertices in the neighborhood of V together. So we have a clique from the vertices in the neighborhood of U. And so we have this formula for domination polynomial of G that is, you see here, is dependent to vertex contraction, deletion of a vertex, and deletion of closed neighborhood of U. And also we have this last term that is a polynomial which is denoted by P sub U. And this polynomial is polynomial that can't dominate instead of G minus U, which do not contain any vertex of in the neighborhood, open neighborhood of U. And we have another recursive formula for domination polynomial. For example, let to denote G with G O dot U, the graph obtained from G by removing all edges between each pair of neighbors of U, and note that U is not removed. And here we have another recursive formula for a domination polynomial of a graph. And Kotek and another colleagues, his colleagues obtained another recursive formula for domination polynomial based on age deletion. And you see age deletion and vertex contraction and so on. Okay, let me to say something about the unimodality of a polynomial that I need later for fair dominating set. We say that a polynomial P of X, A0 plus A1X plus AN X to the N is unimodal if the X is K, which is called a mode of the sequence, such that we have this inequality that you see here. We have a increasing, and after AK we have decreasing situation. And also we say a polynomial is logarithmically concave or log concave if for every K we have this inequality that AK to the 2 greater than or equal AK minus 1, AK plus 1. For example, of unimodal sequence, as I think you know, that binomial coefficient n choose I is a log concave sequence for fixed n and I between 0 and n. And also the sequence of a Stirling number of the second kind is log concave. It is easy to check it. And maybe a basic approach to tackle the unimodality problem is this theorem, which is famous as Newton's inequalities, that says let A0, A1, A, and be a sequence of non-negative numbers. If this polynomial sigma AKXK has only real roots, then we have this inequality, and so we have AK to the 2 greater than or equal AK minus 1, AK plus 1. And so this sequence is log concave. And since every log concave sequence is unimodal, so we have the unimodality of the coefficient of this polynomial. And note that we have this relation between the constants of real rooted polynomial, and which is subset of log concave sequence, and every log concave sequence is unimodal. But the converse is not necessarily true. For example, you see here we have a sequence which is a unimodal, 1, 7, 10, 3, and 2 is unimodal because from 1 we have increasing to 7, and 7 to 10 also we have increasing, but after 10 we have decreasing 10 and 10 and 3 and 2. But note that this is not log concave sequence because 3 to the 2 is not greater than equal to 2 times 10. Okay, so every log concave sequence is unimodal, but the converse is not true. And there are some techniques to tackle the unimodality problem. Let me to say that checking the unimodality problem and proving the unimodality is not easy subject in the mathematics and in the graph theory. But there are some techniques that tackle this unimodality problem. For example, some techniques in real analysis, and second one is some techniques in homological algebra, and the third one is combinatorial argument. Just let me to say about the history of unimodality. You know the chromatic polynomial and coloring the graph. A proper coloring is an assignment of colors to vertices such that each vertex has one color, and no adjacent vertices have the same color. Okay, and you know the chromatic polynomial, which denoted by PG and lambda, is the number of proper coloring of a graph with lambda colors. And Reed in 1968 guessed that this polynomial is a unimodal, and after I think about 50 years, John who has won Fields Medal for I think 3 years ago, proved that the chromatic polynomial graph is a unimodal polynomial. And we have this conjecture from 2009 that says that the domination polynomial of any graph is unimodal, and maybe this theorem is a very good idea to tackle this conjecture. And you see the problem is this problem has solved for about half of coefficients. That says that if G is a graph of order n, then for every I between 0 and half n, we have this inequality. The unimodality of domination polynomial studied well, I think, in the papers, especially recently. But let me to say and state some result about the unimodality. For example, you see here a result that says that if we have a graph with exactly 2 domination roots, means domination polynomial have just 2 roots, then this graph is of the form of corona HC with K1, and so this kind of graph are unimodal, and this domination polynomial obviously is unimodal, and also the domination polynomial of any graph corona with K1 plus TK1 is also unimodal. And you see here one kind of graphs that have exactly three roots, three domination roots, and these roots are 0 and -2 plus minus a square root of 5/2, and this graph have this root, and the domination polynomial is as like this formula that you see here, x to the enter times x to the 2 plus 3 times x plus 1 to the enter. And so the domination of the domination polynomial of this kind of graph is also unimodal. And there are many another result on unimodality that, for example, you see here the domination polynomial of a corona of any graph with complete graph is unimodal. And as another result, if we consider friendship graph, which is join of K1 with n K2, and you see the picture of friendship graph here, and this domination polynomial have this formula, and you see the roots of this friendship graph for order between 1 and 30, and you have this some result on roots. For example, we have this one that says that for every odd natural number, no non-zero real number is the domination of friendship graph, and we could prove that the domination polynomial of friendship graph is unimodal. Okay, and also the domination polynomial of friendship plus UV, where U is the center vertex, is also unimodal. Okay, and recently Beaton and Brown in Canada proved that if we have a graph of order n and k greater than or equal half n, and this parameter which defined here, Rk is the number of dominating set of cardinality chi over n choose k greater than or equal this number, then we have this inequality. Okay, in particular, if k is ceiling n over 2, then domination polynomial is unimodal. And we have this interesting theorem that says if G is a graph of order n with minimum degree delta, which is greater than or equal to log of n in base 2, then domination polynomial of G is unimodal with mode at cln over 2. Okay, let me to start. Fair dominating set and fair the enumerating or counting fair dominating set of graph. Note that after the counting the dominating set of graph, many researchers like to count another kind of dominating set. For example, there are some papers on counting the number of total dominating set, some paper on counting the strong dominating set and so on, but not that I think no any dominating set have worse to count, I think, because some of them just have one term, two terms, and very small, very few number of terms that obviously is not good problem to study. But for fair, I think is good problem to study their counting. Define the fair dominating set, okay? Consider a number integer k, if k fair dominating set, abbreviated KFD set, is a dominating set such that the cardinality of intersection of D with open neighborhood of V is exactly K. For every vertex V which is not in D. And a fair dominating set or FD set is a KFD set for some integer K. And as usual, the K fair domination number of a graph, which is denoted by FD sub K, is the minimum cardinality of a KFD set. And the fair domination number, which is denoted by FD of G, is the minimum cardinality of an FD set in G. For example, you see here this graph with 11 vertex, and this black vertices is a 2 FD set because every vertex which is not in D have 2 vertex in D. Okay, because for example here the open neighborhood of 1 include 6 and 7, and for another you see we have exactly 2 vertices in the neighborhood of any vertex. And for this cycle of order 7, you see 1, 2, and 5 is a 1 FD set. Note that maybe a dominating set, is not a 1 FD set or is not 2 FD set. For example, let me to show you the first example here before that I think I showed for the domination number. Let me do, yes, this, if you consider this figure here, and this dominating set, 1, 8, and 10, obviously this set is not one fair dominating set, okay? Because, for example, the vertex 7 have 2 vertices in the neighborhood. And also is not 2 FD set, because, for example, the vertex 4 have just 1 vertex. So maybe a dominating set is not one fair dominating set or 2 fair dominating set. Okay. Okay, as another example, you see here, it is obvious that the set 1 and 3, 1 and 4, 2 and 3, and 2 and 4 are dominating set of P4 with cardinality 2. So the number of dominating set of P4 with cardinality 2 is 4. But note that the set 1 and 3 cannot be a 1 FD set because the neighborhood, the intersection, the cardinality of intersection of neighborhood of 2 with D is 2. Also, the set 2 and 4 cannot be a 1 FD set. So we have just 2 fair dominating set of P4 with cardinality 2. Okay, let me say something about the fair domination number. Note that for any graph of order n, the domination number is always less than or equal fair domination number, and fair domination number is less than or equal the number of vertices, and this inequality holds if and only if we have an empty graph. And Caro, Hansberg, and Henning proved that if the complement of a graph is connected, then fair domination number of complement of a graph is equal to fair domination of G. And if complement of a graph has Q component, then the fair domination number is less than or equal n over Q, which is less than or equal n over 2. And they found another upper bound for fair domination number and for graph with order greater than or equal to without isolated vertices. And you see here there is n minus 2 as an upper bound for fair domination number of a graph. And this number is sharp, but not that. I think characterization of graph G with this equality is open problem yet, I think. In other words, we do not have the characterization for graph G that ft of G is exactly n minus 2. And you see in this proposition about a regular graph, if G is a regular graph on n vertices, then fair domination number of the graph is less than or equal n minus c times log of n for some c. And also there are another result for FT set and fair domination number that you see here that says this observation say that every one fair dominating set in graph contains all its strength support vertices. Support means the vertex which is adjacent to a leaf of graph, and strength support means a vertex which is adjacent to at least 2 leaves. Okay. And this observation that says every one FT set contains all its strength support vertices. And similar to or a theorem for domination number, we have this observation that if a theory, I think this T should be a theory that I didn't write here. If T1 is T seek with K1 of order n, where T is a theory, then fair domination number of this kind of graph is exactly n over 2. In other words, this kind of graph have equal domination number and fair domination number. And this is similar to or a theorem for T that says if T is a theory of order n greater than or equal to, then if the sub n of T is less than or equal n half, and equality holds if and only if the theory is in the form of corona of another tree with K1. And so if T is a theory of order n, then fair domination number of T is less than or equal n half. And also we have the equality for theories of the form corona K1 with another tree. Here you see Nord-Ashgadov inequality for fair domination number that I skip them. Let me to skip some of result because of time. Just let me to say about the cactus, the fair domination number of a cactus graph. If it is a cactus with co-cycles, then you see here an upper bound for fair domination number of graph. And also, you see here, if G is a unicyclic graph of order n, then if d sub 1 is less than or equal n plus 1 over 2, that we have the characterization for equality of this inequality. And also, we have another upper bound for fair domination number of outer planar graph. For outer planar graph, the fair domination number is less than or equal 4m minus 3n plus 3 over 2 minus r, where m is the size and n is the order and r is the number of strain block that I defined before, but I skip here. Okay, similar to domination polynomial, we can have fair domination polynomial, or maybe it is better to say just we want to count the number of fair dominating set. For example, you see here we have a cycle C7 and we have 7 fair dominating set with cardinality 3. Note that any vertex which is not black have just one intersection with black vertices in the neighborhood. Okay, now I want to ask this question that how many fair dominating set paths have? We thought that this is should be not difficult problem, but we saw that this is not easy, and me and my former PhD student, Mariam Safazadeh, thought about this problem, and Mariam found that there is a relation between the number of fair dominating set of paths and cycle with composition and partition of a number. Let me to recall the definition of composition of a number. A composition, as you know, a composition of a number is an order collection of one or more positive integer whose sum is n. And the number of sum n is called the number of parts. And two sequences that differ in the order of their terms define different composition. This is a different difference between composition and partition that say about it later. For example, we have 16 composition of the number 5. So here I recalled the composition of natural number. Okay. Now I ask this question that how many fair dominating set with cardinality k a path Pn can be have? Okay. How many fair dominating set with cardinality k a path Pn can be have? To construct the fair dominating set, we have this algorithm that says if n minus k is odd and n is less than 2k, then we construct the fair dominating set based on two kinds of composition of the number k. First, we composite the number k to n minus k plus 1 natural numbers. For example, we composite the number k to t1 plus t2 plus tn minus k plus 1 over 2. And we define some family which denoted by A, based on the composition K, as follows, that A is the union of A1, A2, and so on, where A1 contains T1 consecutive numbers from 1 to n, and the set A2 contains T2 consecutive number from bracket n minus A1, and so on. And note that here we have this condition that the induced subgraph with AI and the induced subgraph of AI plus 1 should have distance exactly 3. It's not so, maybe it's so easy to explain this structure. And if, okay. Note that for the past, we have two cases for every set in this family. We have two cases, one in F and n is not in F, and we denote this family by F1, and the second one is not in F and n is in F. Okay, and we denote by F2. And we compose it. Again, we composite the number k to n minus k plus 1 natural numbers. And also, again, we define another family which is denoted by B. And B is the union of B1, B2, and so on. And B1 contains T1 consecutive numbers from n. And similar to previous slide, but here, the induced subgraph of BI and BI plus 1 have distance 2. And you see here another structure that and another family which is denoted by C. And let me to skip this, but note that here also the induced subgraph of CI and CI plus 1 have distance 3. And here, another family which is denoted by D, and this family based on this composition that you see in the above of slide. And here, the induced subgraph of DI and DI plus 1 have distance 3. And finally, based on this composition of k to n minus k plus 1 non-negative number, we define another family which denoted by E, and is the union of some EI and the induced subgraph of EI and EI plus 1 have distance 2. And we have this result about the cardinality of this family that you see here in this slide. And so we have this theorem about the number of fair dominating set of paths of cardinality K obtained as follows, that if n minus k is odd, then the fair domination, the number of fair dominating set of Pn with cardinality k is 2 times cardinality of this family plus the cardinality of family B if n less than 2k, and 2 times the family of A for n greater than 2k. And also you see here for n minus k even that we have this result for the number of fair dominating set of Pn with cardinality k. As I said before, counting the number of fair dominating set of paths is not easy, and maybe stating an example here is not bad. Let me to apply the theorem to obtain the number of fair dominating set of P8 for some K, obviously we can obtain the number of fair dominating set of any graph P8 for K between 3 and 8. We start from the fair dominating set of with cardinality 3. Note that here n is 8 and k is 3, so n minus k is odd, and n is greater than or equal to k, which is 6. So the algorithm say that we have two kind of fair dominating set, f1 and f2, where one is not in f1 and 8 in f1, and another one is 1 in f2 and 8 is not in f2. Okay, and Hamid, I think I have 20-minute time. Okay, Hamid, everything is okay, I think. Based is not that based the composite of the number 3. We composite the number 3, which is a k, to n minus k plus 1 over 2 natural numbers, and that is just this composition. 3 is equal to 1 plus 1 plus 1, and by some explanation, we have these two fair dominating set that you see here. If you consider these 3 black vertices, then the induced subgraph by this one and the induced subgraph by 5 have distance 3, and so you see here the fair dominating set of pass with cardinality 3 is 2. Okay, and in the slide I obtain another number of fair dominating set with another cardinality. You see here for finding number of fair dominating set of P8 with cardinality K, here we should find these two family C and D, where C and D are made as follows, depending to composite of this number K to these two natural number. That you see we composite for here 1 plus 3, so we choose just one vertex here and 3 vertex here, consecutive vertex here, and another one is we choose 2 consecutive vertex here and 1 vertex here. And note that here the distance between this induced subgraph is 3. And again, by composite of number, you can find the cardinality of family D, and finally we have this result that the number of fair dominating set of P8 with cardinality 4 is 6. And you see for 5, the fair dominating set with cardinality 5, and we have 12 fair dominating set with cardinality 5, and we have I think 16 fair dominating set of cardinality 6, and finally 8 fair dominating set with cardinality 7, and 1 fair dominating set with cardinality 8. Okay, and you see here a table that show us the number of fair dominating set of paths for n between 1 and 13, and cardinality also between 1 and 13. And you see here this have a good interesting relationship with this number, and we think that this number have, you see here, we think that these numbers are unimodal because, for example, for row 13, we have some 0 here, 5, 20, 36, 63, and until 106. Then we have decreasing here, 106, 102, 56, and so on. And we have this conjecture that the sequence of the number of fair dominating set of paths is unimodal. And here we have some result for the number of fair dominating set of a cactus, which is a triangular cactus. And you see some result about the fair dominating set of cactus Tn, and some of them related to fair dominating set of paths, the number of fair dominating set of paths. And here you see some result about the number of fair dominating set of complete bipartite graph with the same number of vertices in the parts. For R is odd, and here for R is even, we have this result. And for the cycle, again, we have a bad situation, and it's not easy to count the number of fair dominating set of a cycle, and we need again to consider a partition of a positive number that, for example, we denote by this number P n semicolon x1 to the t1, x2 to the t2, and xk to the tk, the partition of the number n exactly to k parts x1 and xk, where ti is the number of xi in this partition. For example, when we write P of 7 semicolon, should be semicolon 1 to the 1 and 2 to the 2, it means that we have this partition 1 plus 2 plus 2. And by this partition of a number, we have constructed and fair dominating set of cycle similar to paths, and we have this result that if n minus k is even and n less than or equal to k, we have this construction that fair dominating set of cycle Cn with cardinality k obtained by union of A and B and so on. And this is an example for I think C8, and here we have a theorem for the number of fair dominating set of cycle that you see here. We have a parameter P1 and P2 that I explain here in this slide about this number that which is dependent to the partition that I said before it. And you see here a table which give us the number of fair dominating set of cycle with cardinality J, and you see here unfortunately this number is not unimodal. For example, in the last row you see here 3 and then 0 and 42, 36 and so on, and this is the first kind of dominating set that I see, then their number is not unimodal. So the fair domination polynomial of cycle is not unimodal. And just as another result about the regular graph, we have some results. For example, this one say if G is a vertex transitive graph, and then the number of fair dominating set of G with cardinality I is equal to this n over I df to the VG and I, where this notation is cardinality of a family of all fair dominating set with cardinality F, which contain the vertex V. And you see here for K regular graph of order, and we have the fair dominating set of G with coordinate n minus 2 is exactly n choose 2. And for Peterson, you see fair domination polynomial, and you see this polynomial is not unimodal, okay? Because it's not unimodal or is unimodal. It's not unimodal because we have 20, 12, and 15, so it's not unimodal. So the fair domination polynomial of cubic graphs of order 10, especially Peterson graph, is not unimodal. And it is interesting that all cubic graphs of order 10 determined uniquely by the fair domination polynomial. And we have some result about the power of graph, and you see here the fair domination number of power of a cycle obtained by this result. And we have the number of fair dominating set of Cn to the 2 power 2, and there are many interesting relationships between this number, but we couldn't find a close formula for the number of fair dominating set of power of cycle. And this is the number of fair dominating set of Cn to the 3. And so let me to say the fair domination polynomial is not unimodal. Okay, thank you so much, everyone, and I hope this presentation be useful for you. Thank you, Hamid. If any question.
Professor Alikhani, thank you very much for your nice presentation.
You're welcome.
And we really enjoyed. Okay. Dear friends, if you have any questions, please turn on your mic and express your questions. We would be happy to listen to your questions.
Yeah, hi. Yeah, I have a question. May I ask?
Okay.
Hi, Elena.
Yeah, hi, Saeid. Hi. Yeah, it is really very nice talk. Thank you so much. Well, I'm interested in your results on vertex transitive graph. Would you please show me the page number 80? So there is a theorem about
this one.
Yeah, this one. So I'm just wondering which group theoretical properties did you use to get this result? Because since it is vertex transitive graph, this means that there should be some background, right? Yeah.
Yes. Elena, we didn't consider any group theories. No. It is good, but this is good subject that tagged to the domination polynomial or maybe fair domination polynomial of vertex transitive graph is a very good subject. But I didn't consider this kind of graph. Just here we found that the number of fair dominating set for counting the fair dominating set of a graph. It is easier for transitive graph, but we didn't add any another result for this kind of graph. But this is good suggestion, maybe for Cayley graph and for
yeah, I think so. Should be that say automorphism group of vertex transitive graph should be useful here, right? Yeah. And another question is: so is there some relationships between this result for vertex transitive graphs and for K regular graphs? Because the next theorem on this slide the same slide. You also have got some result for K regular graphs. So are there any some relationships between approach you use to get results for vertex transitive graphs and for regular graphs?
Actually, I don't know. This is a big my problem in the domination theory because about it is about more than 15 years that I work in domination polynomial and counting, but I do not have a very interesting result about the number of dominating set, just dominating set of a regular graph, you know, and unfortunately, maybe very strong mathematician can take this problem and solve this question. Thank you, Elena.
Yeah, okay, thank you. Thank you very much. It is really very
Okay.
nice. Thanks a lot.
Okay, you're welcome. Thank you.
Okay, Professor Alikhani, thank you very much again.